On soon, but in the interest of time, we're going to go ahead and get started. Welcome to the sixth session of ARCS Forward and the National Scholar Speaker Series. It's really nice to see so many of you back from summer and here on the Zoom screen today. Wish we could be meeting in person more often, but this is a wonderful way to be able to bring programming to the ARCS community as a whole. Thank you for joining us. And just to note, this session is being recorded. I'm Chris Simpson Brent, and I'll be moderating today's session. I've been an active member of the ARCS Northern California chapter of the ARCS Foundation for 24 years. In fact, I'm a second generation ARCS member, joining and sharing my mom's commitment and passion for the ARCS mission. I've served in many roles in the Northern California chapter, including a few years as president. And I continue to be enthusiastically engaged in leadership positions, both in the chapter and at ARCS National. Today's topic, entitled Computational Chemistry and its Environmental Applications, will feature our newest Hall of Fame inductee, Dr. David Dixon, along with ARCS San Diego scholar, Kyle Engel. And it's great to be welcoming back this series after our summer break. ARCS Forward is a recent initiative of ARCS Foundation. Our first session was in May of 2021. We established the ARCS Forward National Scholar Speaker Series to inform our audience about science topics that are relevant and interesting to both science and non-science people. By harnessing talent from across the ARCS Foundation network, we've been able to bring together scholars from various ARCS chapters who are researching and working in similar areas of study to share ideas and inform us about their work. Past sessions, including those on prostate cancer, the environment, and public health, have been well attended and highly informative. In case you're new to our organization, ARCS stands for Achievement Rewards for College Scientists. The mission of ARCS is to advance science in the United States by providing financial awards to academically outstanding U.S. citizens studying to complete degrees in science, technology, engineering, and medical research. For more information about ARCS Foundation, please check out arcsfoundation.org. Today, I'm delighted to welcome a very special and accomplished ARCS scholar, Dr. David Dixon. Dr. Dixon was an ARCS scholar in 1968, while an undergraduate at the California Institute of Technology. He joins an elite group, including 12 other ARCS alumni, who have been recognized for outstanding contributions to science by their selection to the ARCS Alumni Hall of Fame. Dr. Dixon was chosen as a member of our Alumni Hall of Fame for his exceptional contributions to the advancement of science and U.S. competitiveness in STEM-based innovation. His work in the area of computational chemistry is groundbreaking, and he's developing alternatives to chlorofluorocarbons, a mouthful, that have restored and protected the ozone layer. Dr. Dixon is the Robert Ramsay Chair of the Department of Chemistry and Biochemistry at the University of Alabama. Previously, he worked at DuPont Central Research and Development and Pacific Northwest National Laboratory. He joined the University of Alabama in 2004. Again, on behalf of the ARCS Forward Committee, thank you all for joining us today. As you listen to these speakers, please feel free to enter your questions into the chat. There will be time for Q&A at the end. So now please join me in welcoming Dr. David Dixon.
Okay, I'm going to try and get this thing set up now, so it'll take me 1 second here. Okay, hopefully everybody can see the screen.
Yes.
Can everybody see the screen?
Yes, it's clear.
Okay, so thank you very much for the invitation to give a talk today. And I'm going to tell you a little bit about how we use computational chemistry in addressing issues in energy and the environment, because they're completely interlinked and intertwined. I'm going to try and keep it at a level that I think will be interesting to a broader range than if I were just talking to my compatriots in computational chemistry. The work that I'm going to the work that we do now is heavily sponsored by the Department of Energy. We actually have grants in geochemistry, heavy element chemistry, which is basically stuff that you would use for nuclear reactors or cleanup, catalysis, and also then from a Georgia Tech effort, an Energy Frontier Research Center on capturing acid gases from things like combustion. And we also have a new DoD SBIR looking at advanced fuel technologies. So a little of my life background. I was born in Houston, Texas, and then my dad got redrafted back into the government service. He was an OSS in World War II. He spoke Chinese, and along came Korea, so he got grabbed back into the government service. And so we went to the Philippines and then to Hong Kong and Taiwan, where I spent most of my first through fifth grade. After that, we moved to Connecticut, and then I went on to college at Caltech. And the picture is Hong Kong is my brother, my sister, and I, probably somewhere in the mid-50s, dressed in our British school uniforms that we'd have had to wear at the time and wore every day that we went to school. I'm giving you pictures of Dick Marsh, who was one of my undergraduate research advisors. Dick is shown there with Linus Pauling, and then Jack is Jack Beecham, who was another one of my undergraduate research advisors. I did two different projects. I then went off to grad school at Harvard, where I worked with Dudley Hirschbach and Bill Lipscomb. The years on their, the 1986 and 1976 correspond to the years that they won their Nobel Prizes. And I helped work on some of the work that won them their awards. I did work in both cross-beam chemistry and molecular orbital theory. And then after that, I was very lucky to be a junior fellow at Harvard. And again, shown at the right there is one other person named Bill. That's not Bill Lipscomb. That's actually Bill During, who was also a mentor of mine. And he's shown there with Leo Szilard, because he was very involved in controlling nuclear weapons. After that, I went off to Minnesota for a little bit and then went off to DuPont Central Research. My sort of managers and mentors there were Bruce, the Santa Claus looking guy, and Ed Wasserman, who had moved there from Bell Labs right around the time that I went. Tom Dunning gave me an offer to go to Pacific Northwest National Lab as an associate director, so I went there, and then went on to be a Battelle Fellow for a while, and then went to the University of Alabama. And shown here, the people who attracted me to Alabama was Bob Witt, the president, Bob Olin, the dean, and then Joe Thrasher and Bo Artewengo, who were faculty members in chemistry. And I had worked with Bo at DuPont, so he's been a colleague of mine for over 40 years. So I won a bunch of different awards. I'm very, the first two are shown are actually ones that I would not have probably gotten had it not been for my ARCS sponsorship and fellowship. I was an ARCS scholar from 1968 to 1971 for 3 years. I really appreciate all the support that I received as an undergraduate, because it let me actually be involved in research and many other things that really was helpful to advancing my career. And then we've gotten a few other awards, and the most recent one, of course, which I'm very proud of, is the 2022 ARCS Alumni Hall of Fame nomination. So I really appreciate everything that ARCS has done for me in advancing my career. Let's now then go ahead and look at a little reasons why we actually care about what's going on in terms of energy and its impact on the environment. If we think about the top little equation there, which says that the world energy consumption rate, so that's simply looking at how the energy changes with time, our use of energy changes with time, is equal to the global population times the gross domestic product per person times the energy intensity for the gross gross domestic product. So what we see here then is we can't change, we can control the population, we can't do much about that. We want to keep improving the second term, which is we want to have everybody have a better lifestyle. So the only thing we do to manage energy is to basically make things a whole lot more efficient. And that's what I think one of the goals, and we have to think about broadly in terms of what we're trying to do science to manage energy and environment. And obviously they're completely interlinked and intertwined, because it's our use of energy and how we use it that impacts the environment. Shown in the bottom left here is one sort of diagram of showing sort of how we use energy and how we can look at biofuels, right, versus coal versus oil and so forth. Biofuels, of course, are things like wood. Burning wood is, of course, decreasing. We've increased a bit of our use of coal. Our oil, of course, is increasing again. And then we've got, limited amounts of hydroelectric and nuclear, and natural gas is serving sort of an intermediate. As shown in the upper left is an interesting diagram showing how our use of oil changes with the gross domestic product. And if you look right around 1990 to 1994, you can see there's a big dip there. And of course, that's when the Soviet Union fell. And so we can track our utilization of oil tracks very much how our gross domestic product changes. And we can then see that this will even track, you can look at the recession in 2009 and how things changed there. And the bottom basically showing that the slide to the left again, just to give you a feeling how important the oil is. And the fact is that oil, coal, and natural gas show a dip in 2009. Everything does because of the recession. So how we use energy is very tied to what we do in the environment. We're going to see the same kind of effects if we were to look at what's going on underwent when COVID took over. Okay, so for my misspent youth, hopefully some of you will recognize this. If you were a reader of Mad Magazine, and he always said, "What me worry?" And the idea is that we should be very worried about what's going on in the environment. And so in the upper left is showing atmospheric CO2. The little oscillations are not just random data. They're actually showing summer and winter. And we see that there's different amounts of CO2 released and absorbed during those time periods. We also see that the ocean carbon dioxide is absorbed by the ocean. The ocean is one of the biggest sinks and storage rates for CO2. CO2, of course, as we absorb it in the water, you're all aware what happens, right? We all drink soft drinks, makes them acidic. So we're making the ocean more acidic as we put more CO2 out. The ocean absorbs more and makes it more acidic, which has consequences. We can see that the upper ocean temperature is increasing. That has consequences. And then we can see that things like snow cover and sea ice, of course, are going down, which have significant consequences of what's going on. And it's not just carbon dioxide we have to worry about. There are lots of other aspects of this we'll mention briefly in my talk. And then we can see then that the global sea level is, of course, average sea level is changing as well. And so there are, many small things that are accompanied mostly by our use of energy, but there are other aspects of improving our lifestyles that have impacted climate change and global warming. So we have a broad range of efforts in my research group. I won't go into detail on all these, but they're very much tied to looking at energy aspects. How do we make chemical energy? How do we make chemical reactions use less energy and produce less wasted products? That's catalysis. Can we design new nuclear fuels? We're looking at that. Can we capture things like carbon dioxide or other acid gases like NOx, NOx, which is important in smog, or SOx, which is important in acid rain? Can we use hydrogen to fuel cars and to fuel other programs for propulsion as well as for fuel cells? And that's an experimental program we have going on. We're looking at how we can capture CO2 on minerals. Then we have to worry about things like the atmosphere, clean water. And then we worry about not only about subsurface chemistry, we also worried about nuclear site cleanup because I worked on the Hanford site when I was at Pacific Northwest Lab. And then the other areas are just sort of things we do behind the scenes to make sure that our methods that we can use to tackle the big problems are working correctly. Why do we even bother to do theory and simulation? Well, we can enhance our understanding of known systems. This is why we use computers. That's sort of a first simple thing. We can get insights. We can help direct new experiments. And what's happened, I think, over the last sort of 2 or 3 decades is computers have gotten better, but also as the computational methods have gotten better, we can actually completely replace experiments that are too difficult, too dangerous, or too expensive to do. We can look at new parts of space and time that we can't readily connect with experiment, and we can take limited experimental data and really get into new areas of science in terms of looking at different time domains and different spatial domains. One of the key things that we want to do, though, is to make sure that we get the right answer for the right reasons. What we do in my group, and you'll all see more about this from college, we basically solve the Schrödinger equation. We want to know what the heck electrons are doing in molecules. And that's where it looks like it's a simple equation, but it's not really very, very soluble. So let me take a little digression here and talk a little bit about what people have said about solving these methods. Okay, so back in 1830, a famous French chemist, Comte, says, if mathematical analysis should ever hold a prominent case in chemistry, an aberration which is happily almost impossible, it would occasion a rapid and widespread degeneration of that science. Obviously, computers have changed all that, and we not only do experiments now, we couple the two experiments and computation together to sort of take us into entire new realms. Dirac, who received the 1933 Nobel Prize for Physics with Schrodinger, basically says, if I could solve the Schrodinger equation, I could understand all of chemistry. And he says, but I've got no idea how to do it. It's too complicated to do. And remember, at that time, nobody has a computer that's going to be able to let us compute anything. Computers don't come along until basically in World War II, when they were needed to understand how to build atomic weapons and track neutrons and what they were going to be doing. Okay, so a couple of months after I'm born, Time magazine says, here's your career, David. The hazy paths of electrons rolling around a nucleus and the structure and reactions of complex molecules are practical computing assignments for automatic calculating machines. Okay, that's a pretty impressive statement for Time at the time, because there really weren't any computers around, and they really even hadn't published the first papers on how to do this, which actually are published in 1950 and 1951. And then Boyce comes along a little bit later and says, right around the same time, says, we just need to figure out how to do the computing and how hard it's going to be. There's been a lot that's gone on since then. One of the things, and this is a little digression, sort of a freshman chemistry one, but we do worry about accuracy in our calculations, because if you make an error of about 1.5 kilocalories, which is a pretty small number, you already make errors in terms of being able to separate something by a factor of 10. Or we may get we have the same kind of error impacts how fast a reaction is predicted to occur, and a factor of 10 is a big deal. That can make a difference in a business environment of whether the product can be manufactured cheaply enough. And in fact, factors of 2 and 4 have an impact in terms of what you can actually put into the atmosphere. So getting accuracy is something that's important, and we worked a long time on trying to get that correct. Another thing we're worried about is basically the other idea is, what is uncertainty? So we have uncertainty not only in what we do in our calculations, but we have to design physical models that can be uncertain. We're trying to understand how do we do that? Because uncertainty is a huge issue broadly across science, especially in environment. Uncertainty is what drives what we want to do. And that's involved in the health aspects from the environmental science, as well as then in terms of how chemicals are going to impact what we do in real life. Okay, so our computational methods here, I'm just going to show you a little plot here that computational chemistry is sort of been and theoretical chemistry has been a big deal according to the Nobel Prize Committee. I mentioned Schrodinger and Dirac in physics for writing the Schrodinger and Dirac equations, which were what we try to solve. We solve the Schrodinger equation most of the time for electrons in molecules, but Dirac is what we need when we want to go to heavy elements. We have to actually include the effects of relativity, which we have to worry about. Linus Pauling in 54 gets it for valence bond theory. Robert Mulliken for developing molecular orbital theory gets in 66. Walter Cohn and John Popel in 98. Walter gets it for density functional theory, and John for developing a wide range of molecular orbital theory methods, plus implementing them into software that everybody can use. And the most recent one was the prize for molecular dynamics and mixing molecular dynamics electron structure for Martin Karpeles from Harvard, Michael Levitt from Stanford, and Arya Barshal from Southern California, University of Southern California. So, this has been an area that's been important. And this runs across a broad range of levels. We worry about the worries I mentioned about the accuracy and cost. That goes up as we go to the top, and as we get more approximate methods, we can go to much larger systems. We mostly tend to stay in that top upper box, but we sort of dabble in some of these other ones to try and address the problems we want to solve. Okay, now let's go ahead and talk a little bit about refrigerants. So this is work for me that goes back almost 40 years, because when I started at DuPont, they were a huge manufacturer of CFCs. As you could start to see what's happening in the early 80s, people were worried about what was going on with CFCs in the atmosphere. So one Christmas, I was able to get access to all the company's business computers and started calculating properties of fluorocarbons. Why do we care about CFCs and their replacements? And this is shown here. We worry about things like, we have fire suppressants, we have things like HVAC, high vacuums, in terms of heating and cooling, and we have refrigeration. So refrigerants are a big deal. They're sort of sit there behind the scenes, but the big problem about them is that we need them, right? I mean, nobody would think about wanting to live in Florida in much before the 1920s, because the first real air conditioning is going to come out in the 20s and 30s and 40s because of the development of CFCs. So, very many places are really hot. We like to have air conditioning in the summer. And also more than 75% of our food involves refrigeration systems. So we have to think about what we're going to do to get refrigerants that don't impact the environment. So the top compounds here, especially let's say 134A, are compounds that don't deplete ozone, but do contribute potentially to global warming. In the second ring are basically the interim kinds of materials where people are looking at various kinds of more reactive hydrofluorocarbons that can react in the atmosphere readily and decompose, and that they have lower global warming potentials, and we can then use them potentially. And then in the bottom then are shown on the sort of the left-hand side in the green circle are going to basically be the HFCs that are more reactive, but there's some flammability issues. Whereas the other ones, some of these ammonia, CO2, propane, and things like SO2 go back to refrigerants they had in the 1910s and 1920s that we got rid of because nobody really wants to have an ammonia leak from your refrigeration in your house. One of the problems with refrigeration systems is that eventually anything you put in a refrigeration system is going to leak into the environment. And that's why we have to be very concerned about what goes on with refrigeration systems. So how does refrigeration, what does it do? What do we have to look at here? The upper left diagram basically shows what our levels of ozone are going to be. And we can see that in the sort of in the stratosphere where there's this big bump in the ozone layer. That's when we have to have ozone there up there. We want to have it there because it absorbs ultraviolet radiation, it decomposes into oxygen atoms and oxygen molecules and prevents UV radiation from reaching the Earth. If we don't have ozone, it would be very difficult to live on the Earth because so much radiation would reach the Earth's surface. How does this work? Is sort of shown on the bottom screen, left-hand side, is it basically all of the stuff we put in the air, basically eventually will get down sort of to the tropics and the equator where it's hot air rises, it goes up to the stratosphere, and then gets moved around by various currents in the stratosphere and the upper troposphere and comes down at the poles. So the poles tend to be collect pollutants, and we tend to send stuff up at the equator. The CFCs, which were these great refrigerants, they weren't toxic. They were, they were safe. They were great refrigerants. They were stable. They could do all kinds of things, but they don't decompose in the troposphere. They go up to the stratosphere. They release halogens like chlorine. And when they do that, then that can react with ozone to deplete ozone, as I've sort of shown here on the right-hand side. We have bromine that come from halons. Halons were fire extinguisher systems. Their ozone depletion potential is 40 times larger than that of chlorine. And then, of course, then you also have methyl iodide. Iodide can come from two places. One is coming from the marine boundary layer, which we'll hear some very nice work on in terms of organic systems in the marine boundary layer from Kyle. Whereas if we look at methyl iodide, that was being used as a fumigant for strawberries and other kinds of fruits. And yet that's a compound that can then get up into the atmosphere, and iodine is even more ozone depleting. What are the kind of things we have to think about in designing a new refrigerant? We have to worry about timing, and then we have to make sound decisions for what we're going to do. In terms of safety, we have toxicity and flammability. In terms of the environment, you have to worry about stratospheric ozone. How do these compounds decompose in the troposphere? So what do those products do? The degradation products. You have to worry about tropospheric ozone, and we also have to worry about global warming. Performance, we have physical properties and materials compatibility. We also have energy efficiency, and that, of course, then relates to global warming. And finally, then in the bottom is economics. So all these other items have to be addressed before we can even start thinking about what we're going to do in terms of building a production facility. So here's an example then of a production facility. So when we started this work back at DuPont, as you up on the left-hand side were all possible routes to get to HFC 134A that people were designing. And the problem at that point is that none of the thermodynamic data was known, and very little of the kinetic data was known of what routes to take. So what I tackled and started to do was to actually predict all the thermodynamics and as many the rates as we could for that kind of system. If you look in the upper right-hand corner, that's a picture of the HFC 134A plant in Corpus Christi, Texas. That was actually designed using almost all the quantum chemistry we could do. So this plant was designed using quantum chemistry calculations in part, and we were able to get it to operate at 300% of capacity based on what we were able to predict. If you look at the energy that they thought coming from the laboratory measurements in a small tube was going to be, it was going to be about 45 kcals per mole. And we then predicted the activation energy for the slowest step to be about 80, and the actual plant activation energy was 79 kcals per mole. This is many orders of magnitude difference in terms of how the plant operates versus what they thought they were going to get from the lab. What's shown on the right-hand side is how we've advanced, okay, in the last sort of 40 years. The experimental ATCT is basically a machine learning set of work from Argonne National Laboratory by Branko Rusick, where he's collected a huge amount of data and has these very nice accurate predictions from experiment for these kinds of systems. And I'm showing you on the G3MP2 columns that we can actually do an extremely good job compared to experiment with a reasonably modest method for making these kind of predictions. We couldn't do that when we started this kind of project. We had developed all kinds of new ways to do these calculations back 40 years ago. And again, most of these experiments, except for ethylene, didn't exist. Even C2F4, which is tetrafluoroethylene, is a component of Teflon. Those numbers weren't really very accurate. So computing here has really helped us in actually designing a plant that could basically produce a new refrigerant that we could use as a stopgap to get us between the CFCs and where we're going to be today. Another thing that we've looked at is, for example, is that we were interested in things like looking at chlorine oxides. They're very important in the atmosphere in terms of what they can absorb and can they release chlorine or store chlorine. And until we did these results in 2008, everybody thought that the top molecule where you have a chlorine bonded to two oxygen, the chlorine's green, the oxygen in red, was going to be the most stable compound. And we actually showed that the compound ClClO2, the bottom one, where the chlorine is bonded to chlorine and is basically a hypervalent kind of compound, is actually more stable. And this was just not known from experiment. Plus, you can see over on the right-hand side are sort of looking at how these things absorb and how important it is to get these right, because we're really looking at absorption in the tail of these things to see what's going to happen in terms of what's going to be happening in terms of impacts up in the stratosphere. This is some new work we did where we were looking at actually how oxygen then can react to these kind of halogen molecules and what they can do. And what's shown then, and these are the kind of potential energy sources we calculate where we're predicting all the kinds of intermediates, reactants, and products and how the reactions can occur. But what's shown actually on the bottom right is work from 1973, when we actually were able to study this in a cross-molecular beam system as part of my graduate work. And we were able to show then that we were going to have a stable complex in the intermediate. And then, in fact, we were able to predict, but that took us almost 40 years after the experiments were done before we could even get close to predicting what we could see from the experimental work as shown in the oxygen plus Br2. These are very complicated calculations, and we have to worry about the effects of relativity to get the right kind of numbers here because we're looking at very, very small energy differences. I'm going to sort of quickly end up here and talk a little bit about a couple of other examples. NF3O is being considered as an alternative to replace the HFCs or NF3 as a cleaning gas for electronic vapor deposition chambers. So, I mean, you want to go and clean your semiconductor chips. How do we do that? That gas all gets released to the atmosphere, and NF3O is being proposed by the Koreans to do that. In fact, we showed is that it won't work. It's going to not decompose in the troposphere and is going to cause problems. And so this is actually a picture of the Aurora Borealis over Churchill River that was taken in March 3rd, 2020. We were, in fact, the reason I know this is my wife's birthday, and we actually took the picture. We're up there to go up and see the Aurora and go see Churchill, and it's a beautiful area to go visit. Especially in the middle of winter, it's 40 degrees below zero this night. But why if we say it's about NF3O, we could basically show that hydroxyl radicals, which are what is sort of the atmospheric detergent, doesn't react with these things. And we showed that these molecules couldn't photodecompose. So these molecules are basically going to get up into the, go all the way up through the atmosphere. They're not going to decompose in the troposphere. So they're going to be significant global warming aspects. And they'll actually look more like NF3, and they're going to be actually have more global warming than NF3O does. So basically the idea was that we shouldn't probably build a plant, which the Koreans are doing, to manufacture this stuff because it's going to have a very significant global warming aspect. It's going to be it has a significant global warming, very much like CF2CL2, which is CFC12, which is one of the chlorofluorocarbon refrigerants. And also then it's going to have a very long atmospheric lifetime. There's nothing up there to decompose it. And so it's going to have a large impact on what's going on. And these kind of gases that go up into the atmosphere and live a long time and can absorb infrared radiation, where water vapor doesn't, have a huge impact in terms of impacting global warming. That's why everybody's so concerned about stuff besides CO2, because CO2 is a very weak global warming. It just doesn't decompose, but there's so much of it. But if now I can add additional perturbations onto the atmosphere by putting up things that have global warming, that's not going to be a good idea. I'm just going to make a couple of comments here on catalysis and why we care about it. Catalysis is basically looking at ways that we can cause reactions to occur with lower energy input, or we want to basically look at things like hydrogen release and so forth. The reason I want to show this slide is I want to give you a picture of where we are. If you look at the slide on the graph on the right, you get to see an interesting thing. We're interested in getting the maximum amount of energy, joules, per liter or per kilogram. We want it in terms of volume or weight. And you can see the lithium-ion battery, which we are looking at for so much stuff, is very inefficient. It's very ineffective in terms of storing energy in terms of how we store electrons. Things like diesel fuel, gasoline, kerosene, and even things like body fat are great ways of storing energy in terms of volume and weight. And the reason is because I can cram electrons into chemical bonds. I can't, if I have electrons in a battery, they got to interact with each other and they repel. But if I can put them in a chemical bond, they can be much more stabilized. So storing electrons in chemical bonds is where we want to be. And catalysis then is a way of dealing with the storage and how we can then manage those electrons and let them do the most useful work. Say, for example, for solar fuels or for fuel cells and so forth. Again, computational science here is very important because experimentally, I can't really probe the place where the reaction occurs in the transition state, and computation is really the only way I can really tackle that kind of problem. Give you some examples of some of the kind of things we can do. Here's some ideas of how I could convert glucose into all kinds. We worked out all the thermodynamics for glucose kinds of chemistry here, but I want to give you, and just to show you, look, there's a lot you can do in terms of basically making predictions about how all these kind of systems work. This, for example, would be how I convert glucose into useful kinds of biomolecules that then serve as precursors either for fuels or for industrial applications. But again, I mean, this is actually just looking at one of those intermediates, glycerin and glycerol. And in this case here, you can see all the chemistry that's being done by different companies like Dow and Cargill Ashland or Huntsman or Cutter or Arkema, in terms of looking at all these possible intermediates and intermediate products that one can make from these kinds of compounds. So this is actually turning out to be a useful way then to map out all the thermodynamics and again, eventually the kinetics for how we can process all of these kinds of materials. And again, theory here gets us all these numbers, and they're much cheaper to do that. Okay, this just basically shows you some of the stuff that comes out of this other kind of work we're able to do here was to solve a 40-year-old problem in looking at how metal atoms can react with fluorine, and we see very specific absorption peaks here. And so this is stuff that actually then we're hoping is going to lead then to the development of chemical lasers with a very specific visible wavelength, which are very hard to do today. Okay, I'm going to end here and sort of give you a highlight then of some of the things that we've done. We can show that computational methods can really tackle the entire periodic table these days with reasonable accuracy. We can predict the properties of refrigerants, including their global warming potential, as well as their degradation in the atmosphere and their ozone depletion potential. We predict the properties of catalysts and develop reaction mechanisms. We've been looking at ways of doing new ways of chemical hydrogen storage, including regenerating the spent fuel. We're looking at how we capture acid gases, and then we can also then look at developing new fuels here. Up on the left is where I spend my Saturday nights in the fall, way up in the upper deck because we don't get good seats. In the middle is actually sort of my latest group picture. This is Kyle's a postdoc and Caitlin was a master's student in my group. They just got married, and then this is the whole sort of extended Dixon group, including staff scientists, their children, wives, and so forth. But they've been very, very helpful in terms of what we do. I've had 30 PhD students, 3 masters, 17 postdocs, and more than 100 undergrads in my lab over this time period. You know, I've got 3 girls and 4 grandkids, 3 actually who come in. I pay them and they work for me in the summer in the lab. And then I want to thank my wife, Chris. This is showing us on the Zambezi River in Zambia near Zambezi, Lower Zambezi National Park in June of this year. If you've never been to Africa, it's a great place to go and visit. And it's been a great thing to tell all of you about some of the work we're doing. I really appreciate all the support of ARCS, and thank you very much for your attention.
Well, thank you so much, Dr. Dixon. I spent some of my summer in Africa too, so I share that that love and that interest. That was excellent. Just your background, your mentors and students, the science, the importance of your work on refrigerants and catalysts, a bit about your family, very informative. Some of it a little scary, but hopeful. And so thank goodness for smart, great people like you and the help of some computers along the way. So we're very proud of you, Dr. Dixon, that you're an ARCS alum and you are the newest member of our Hall of Fame. So thank you. And now we're going to hear from Kyle Engel. He is an ARCS scholar at the University of California, San Diego. Kyle's a PhD candidate in analytical and atmospheric chemistry with a passion for environmental research, and is just at the cusp of a great science career. So welcome, Kyle. And would you start just by giving us a brief introduction and a bit of background on yourself and your work?
Sure, thank you so much. I'm really excited to be here today and be able to share my research with you. Before I jump into that, just a very quick background as I was born in Kansas City. And so I grew up in the Midwest. I went to a school called Truman State up in northeastern Missouri. And then I decided graduate school was a time to branch out. So I came to University of California, San Diego, because I saw there was some really interesting work being done on aerosols there. And I saw that was an area I could maybe contribute and make a difference. So I'm very grateful to all the support I've gotten from ARCS and so many others along the way. And I will be happy to share with you a few of the research stories that I have been working on. Today, I am here to tell you about sea spray aerosols and how these particular aerosols have an impact on our health and our climate. And specifically, we'll be looking at their acidity and what exists at the aerosol surfaces. So, everyone see these slides okay? Perfect, thank you. Okay, so our planet is covered with about 71% with oceans. And every time in those oceans a wave breaks or a bubble's burst, that ejects something called a sea spray aerosol into the atmosphere. So in this photograph of a crashing wave, you can see a lot of tiny little mist droplets. But for everyone you can see, there are hundreds or even thousands of sea spray aerosols that are even smaller that you can't see. And because there are so many bursting bubbles and crashing waves all over the Earth's surface, sea spray aerosols are one of the largest components of what we call global particulate matter, or simply particles in our atmosphere. There are a lot of them. As scientists, we're interested in these sea spray aerosols, or SSA, because in addition to the water and salts you would expect them to have, they also contain a lot of organic molecules that can do interesting chemistry and shape interactions in our atmosphere. We're also interested in them because aerosols in general have a profound ability to impact our climate. If you look up at the clouds in the sky, every cloud that you see is a result of water vapor that at one point in time condensed on an aerosol. But fewer than 1 in a million aerosols can actually act as a cloud seed. So an ongoing study is which ones do that and why. And we also know that aerosols have an impact on our own health. And so with sea spray aerosols being so abundant in number, we also want to consider what impact they might be having on our health. There are a lot of different components to aerosols that we could talk about. Today, I want to focus on their pH. And this is because aerosols in general have been measured to have a wide range of acidities. And acidities range such a broad span that in the science community, we use something called the pH scale to help us keep track of acidity. So I have a pH scale shown there on the right. You can see that things that are often used for cleaning tend to be more alkaline, like your bleach and ammonia. And then right in the middle, neutral at pH 7 would be perfectly distilled water that isn't being influenced by things like CO2. And then on the more acidic side, you get things like your fruit juices and your stomach acids. And in the lab, we also work with quite a few acids to make chemical reactions happen. And one thing I want to note is that in this pH scale, if you go down by 1 pH unit, that means you are becoming 10 times more acidic. So it is a log scale, and we use that because there is a huge range of possible acidities. So when you see something small in terms of pH units, it could still be a pretty big change in acidity. Now, when we think about aerosols, we want to know their pH because that will affect their climate impacts, which I'll be discussing later today, but it's also important when we think about our own health. And the reason for this is that when we inhale aerosols, they end up in different parts of our body. And in general, the smaller the aerosol is, the further it can work its way down into our lung system. And if we inhale an aerosol that's both very small and very acidic, it can dissolve trace amounts of metals in our body and cause something called oxidative stress, which can have negative effects on our lung health. So this is one of many reasons we encourage people to use ventilation when you do cooking. That's a process, especially if you're burning things, that can produce a lot of small and highly acidic aerosols, and it can have a negative effect on our lung health. So something we always try to keep track of is the acidity or pH of these particles that we're breathing in. Now, I was curious about the pH of sea spray aerosols since there's so many of them. And at first, this might seem like a simple question because the ocean itself has a well-established pH. As Dr. Dixon showed, it's a pH of about 8.1, and it's slowly decreasing due to CO2 in the atmosphere. But what's interesting is shortly before I started my PhD, scientists showed that aged sea spray aerosols could be very acidic, having pHs ranging from about 0 to 4. So this seems to be a mismatch with the ocean itself being a pH of 8.1. The problem is when you go out to measure these collections of aerosols, you're mostly measuring aerosols that have been airborne for weeks. So it's very difficult to go out there with a ship and measure the aerosols that are out there and figure out what pH the fresh aerosols were. So a big question that remained in the scientific community is when these aerosols are first emitted, what is their pH level at? And so this is one of the questions I wanted to answer in my PhD studies. In order to do this, I took part in something called Seascape, or Sea Spray Chemistry and Particle Evolution. It was a sampling intensive we did back in summer 2019. And what this looked like is, if you look in this photograph here, you can see some people standing around, and there at the back of the photo is this long glass tank that's full of seawater. And what we do here is we take this 33-meter wave channel and we put in real seawater from the Pacific Ocean. And the reason we do this rather than working on the real ocean is it allows us to control everything. We can control the temperature and the pressure. We don't have to worry about someone coming in with their sunscreen and changing what our results are. So we can control everything nicely and repeat the same experiment multiple times. Now, we were trying to answer a lot of different science questions in this. This was part of a big initiative by the Center for Aerosol Impacts on Chemistry of the Environment. There were over 90 participants, so a lot of different people I could thank, but I want to give a special shout out to Victor Orr. He was an ARCS scholar from my same research group in the San Diego chapter, and he was very helpful in training me on some of the experimental methods for the experimental side of this project. So I wanted to give him thanks because this project ended up turning out quite well. So what we did is we used a combination of experiments and calculations to try to figure out what the aerosol pH was. On the experimental side, I used something called a Moody, which separates out the aerosols based on size, and I impacted them directly onto litmus paper, which is also called pH paper, because the color it turns tells you the pH of what it's interacting with. Now, there were a lot of laboratory controls I had to do to get this just right, but ultimately I was able to take pictures of this pH paper just with my phone, and then I could analyze the color images on my computer to calculate what the pH was. But I wanted an independent measurement of the same thing. I wanted at least two different things to tell me what was going on. So I also worked with people who were using mass spectrometers, and I had them tell me what all the ions inside the aerosols were. And I was able to use this with a model called EAIM, which stands for the Extended Aerosol Inorganic Model. And there's a lot of chemistry that's involved with this model. Aerosols are quite complicated. Within this water droplet, you can have solids forming or redissolving, and you can have also gases moving inside and outside of the aerosol, so it becomes quite complicated. So what we do is we use a chemical model to solve all of these equations at the same time. And luckily, when I did these two, the two of them agreed, and they came out to the same result. And so here's what we found ultimately. In this bar graph, that thin blue line at the top is the pH of the water we had in our wave channel. So it was 8.1, which is the same as the ocean. And then that bar that's labeled TSP, that stands for total suspended particles, which is mainly a measure of the larger aerosols. And we found they were pH 4, versus our size separated smaller aerosols were about pH 2. And these aerosols, you can see I've labeled them on a micron scale. They're a little less than a micron. For perspective, your hair is somewhere between 20 and 50 microns in diameter. So these are tiny, tiny little aerosols. But what's fascinating about this bar graph is this represents a snapshot in time of these aerosols being airborne for just 2 minutes. So what we found was right after these wave breaks and the aerosols get ejected into the air above them, they are very rapidly acidified. So this was an unexpected but really helpful result, and it told us some of the chemistry that's going on with these aerosols. And so with that, we had in hand the fact that sea spray aerosols can be rapidly acidified to low pH levels. And this shaped how we thought about a lot of different things. And so next, I just want to look at one of the specific impacts this has had. I've branched off into a lot of different directions from here, but I think one of the interesting stories ended up being what happened when we started thinking about amino acids and how those might be shaped by this change in pH. So amino acids, there are at least 20 of them that are of interest to the human body, and there are many more that exist. But they are called the building blocks of protein, or the building blocks of life, because a series of amino acids is how you build any protein. I'm showing just 3 examples here, and you'll see that the right side of each of them looks the same. They have an amine group and an acid group, hence the very creative name amino acid. But they all also have side chains that can have very different chemistry in them. Methionine on the bottom there, for example, has a sulfur atom, and it's known that that can do reactions in the atmosphere that change the chemical composition of the air around us. And the reason I was so interested in amino acids is that scientists have found they can be 1,000,000 times more concentrated in sea spray aerosols than in the ocean itself. So something about this process of forming aerosols seems to enhance them into the aerosol phase. But there was a remaining question about what the amino acids did once they were in the aerosol. Did they sit at the air-water interface, residing at the surface, or do they work their way into the core of the aerosol where they're completely surrounded by water? And this was important to us because what's at the surface of an aerosol impacts its ability to collect more water vapor and ultimately turn into a cloud. So what I wanted to do was look at these amino acids that are greatly enriched into aerosols and try to determine whether the amino acids would sit at that air-water interface or if they would be deeper into the aerosol core. And the reason that pH is an important parameter for these amino acids is because they take on a different form depending on the pH of the environment you put them in. If you put them in a highly acidic environment, you will get a cation, where you have a positive charge on your molecule. If you put them in a more neutral solution, you actually get something that's called a Zwitterion, which is where you have both a positive and a negative charge stable in the same molecule. And finally, if you put them in an alkaline solution, you get a form called an anion, although this rarely happens in the atmosphere. So I wanted to mainly focus on the cation and the Zwitterion and see how they behaved at the surface of these aerosols. I once again employed a combination of experiments and theory in order to study this. And I will just briefly first mention that we used 2 different experimental methods to study this, what we call surface propensity. One of them was measuring the surface tension. I could prepare different solutions of amino acids and probe them with a special rod that would tell me how much force was holding that in place. And that surface tension tells you how many amino acids have gathered at the air-water interface. And I also use spectroscopy, which is when you interact light with your sample, and the change that happens to that light can tell you what chemicals are present. In this case, I bounced an infrared beam off the air-water surface, and when that was arrived at my detector, it would have a fingerprint that corresponds to the amino acids. So I'm just going to jump right to the results of the experimental side, just showing a sort of qualitative picture here. This is not to scale, but more just to give you an idea of what's going on. What I found was that when I had a Zwitterion, the amino acid would somewhat reside at the air-water interface, but when I had the cation form, the amino acids were much more driven to the air-water interface. And their hydrophobic side chains would likely be residing there and sort of hanging out in the air. So this is a result I got from some numbers, but I wanted to use computational chemistry to get more specific insights and be able to probe things that you normally can't see with experiments. As Dr. Dixon said, the computational chemistry gives us access to domains both in time and space that it's very difficult to measure experimentally. So with that, I now want to show you this water box. This is a simulation. So what we've done here is you can see in the sort of upper left, we have our amino acid there. There are some ions represented by the green and purple spheres there. And then the water molecules are not shown. There are many hundreds of them, but we don't show them because they would block out all the action. So with that, I will allow you to watch this video here. And you can see that amino acid headed up to the top of the box. So what you just saw was something called molecular dynamics, where essentially what we do is we put every single atom that we want in our system, and then we solve Newton's equations to see what force will be happening to these atoms and how they're going to move through time. So I'll play that movie one more time here in the bottom right in case you want to see it again. But essentially what's going on here is that we are pulling a specific amino acid called leucine from the middle of a water box to the air-water interface, and eventually all the way out of the water. And the reason we do this is we can calculate the energy at every step. And ultimately what we found is that when we have a cation form instead of a Zwitterion, the amino acid is more stable. So that agreed with experiments. It's easier to have the cation at the air-water interface. The other thing we were able to do is gain insight on the exact orientation at the interface. So just like in Dr. Dixon's presentation, the oxygen atoms are red here. And just to briefly summarize what's going on, we looked at every frame where the amino acid was at the air-water interface. And we saw when we have a cation that the oxygen atoms can actually hang out on the side of the atmosphere, versus when we have the Zwitter ion, they stay water side the whole time where they're able to interact with other ions. And this ultimately tells us a lot about how these amino acids can pull in water into the aerosols and change whether these aerosols are willing to become clouds. So with that, I will quickly wrap up here for the first half of the story. If you want to know more about that, we published a couple different places. One of them was a Physics Today article, which I think gives a high-level overview of what we're doing. So if you're interested in the pH of sea spray aerosols, please give that a read. And we also studied amino acids and how they are pushed to the air-water interface. This is some art that my friend Abby made. She was one of the co-authors on the paper. And the reason there's little cars there driving the amino acids up is the title we settled on for the paper was amino acids are driven to the interface by salts and acidic environments. So we added that cover art to emphasize that. I owe thanks to many, many people. Of course, I want to say a huge thank you to the ARCS Foundation for the funding and support, and especially ARCS member Elizabeth Taft, who has taken me to some fine arts events, which I really appreciate. Sometimes I get my head buried in research, so it's nice to do things I really enjoy and get out there into the world. And I just want to thank all of my co-authors and lab mates, and especially my advisor, Dr. Vicky Gracian, for helping make all this research and much more possible. And with that, I know that was a lot of information. So, in addition to questions, I'm happy to answer any emails. Feel free to shoot me an email at kangle@ucst.edu. Thank you so much.
Great, thank you, Kyle. And yes, we are a little short on time, so there'll be opportunities for any of you who have questions to put them in the chat, and we can get back to you if we didn't get a chance to address them here. Your work, Kyle, though, on sea spray aerosols, their acidity is fascinating. We're grateful to have gotten to know you a bit today and to have heard about your research and your insights, and good luck in the future. We do have a few minutes, though, for questions, and we're really we'd like to start by turning this to you, Dr. Dixon. Do you have a question for Kyle to start us off?
Yes, Kyle, have you looked at how the amino acid transitions from a Zwitter ion to the non-Zwitter ion, which is more stable in the gas?
Yeah, that's a great question. So these amino acids, when they're in water, they like to have both a positive and a negative charge, but there are actual truly neutral molecules in the gas phase. And that's something that's still being studied, but my best hypothesis is there's some interesting work that shows acids behave differently at the air-water interface. Even a strong acid like nitric acid may be less likely to dissociate there. So I think it's something called the sea surface microlayer, or the very topmost layer of the ocean. That's going to change the energetics. And when you have hydrophobic things accumulate there, I think it makes it easier for the amino acid to convert to its true neutral form, where it can then be emitted into the atmosphere.
Great. And Kyle, turning the tides, do you have a question for Dr. Dixon before we open it up?
Yeah, I wanted to ask, so, a lot of times in science, we study very specific things. And then in your work, Dr. Dixon, you've been able to apply it to these really large scale things like climate change, where you have a lot of complexity and it's just really a massive system. So what are some of the ways that you're able to take your individual puzzle pieces and fit them into these bigger picture issues like climate change?
So what we're trying to do is get the raw data. We're going to somebody else's model. Our goal is to get accurate data for these very large scale models that are used to predict climate. So we're personally not involved in actually doing the atmospheric simulations, but we are providing the data that is needed to go into models. So as an example, when people were trying to get rid of the CFCs, the model was built on a one-dimensional model. And that model turned out to be the one that Roland Molina won the Nobel Prize for, turned out to not be correct. That's not actually what happens. But that then led to the discovery, in fact, the thing that's very related to your work, of the importance of ice crystals in the upper stratosphere, where these chlorine oxides could collect, and then they would collect in the winter, and then they would get released in the summer, very much like what you're seeing. and lead to the Antarctic ozone hole. So your sea salt kind of stuff is very related to the actual ozone depletion stuff, because it turns out that it's these small ice crystals that make the difference, not basically the gas phase chemistry.
That's fascinating, the interaction between the research that both of you do. We have one general question here that I'd like to pose, and that is, what should we be doing, ARCS and society, to be encouraging more students to go into STEM fields? And whoever wants to take that first.
Okay, I think that what you do is already very, very important. So for example, I forgot to mention, one of my former undergrad researchers, Ashley Everly Hunt, is now actually an ARCS scholar at Washington State, working with one of my collaborators. And so I think that the more you can do to provide students with opportunities to focus on their research in terms of the fellowships you provide, I think is really, really important. I mean, it's going to enable the best students to really get even more research efforts in, and if they don't have to be teaching as well. So I think that all you do in terms of supporting students with these scholarships is very important in moving the whole STEM field forward.
We'll keep at it. Thank you. And Kyle, from your perspective?
I would certainly agree with that. Yeah, I think any support you can provide, and especially any personal touch, goes a really long ways. I liked in Dr. Dixon's presentation, he started off by showing all the scientists who had mentored him around the way. I had the opportunity to teach a summer class this past summer, and I started off each lecture with something I called a scientist spotlight, where I would just show some scientist what they did, maybe some struggles they overcame. And after the course was over, I got a lot of positive feedback about that. So I think a lot of people, they're looking for positive role models, and they're looking for people who are personable. A lot of times the lab feels really impersonal, and even the way we're encouraged to write scientific articles, we have to remove ourselves from all the writing. So every aspect of humanity we can put back into it, I think, goes a long way to show people this is something I want to do and something that I can succeed at too.
Great point. And we often hear that from our scholars. It's not just the financial award itself, but it's having somebody there really rooting for them. And in our case, many, many of us rooting for them. And the mentorship that you all provide for the next generation is huge. So thank you for what you're doing already. And we hope all of our ARCS scholar alums are out there giving that support to the next cohort coming along. So we're going to need to wrap. I want to thank you again, both Kyle and Dr. Dixon, for being part of today's program. The work that both of you are doing is impressive, and clearly what you're already engaged in will continue to do will have a huge impact on our world, and also will motivate that next generation of scientists. We appreciate your giving back to ARCS today by sharing your career highlights and your insights and your research. And we thank everyone in our audience for participating in this session, your attention, your curiosity, and just being supporters of science and science education. We will send out a link to this recording so that you can either re-listen to it to get all the good nuggets and also to share with others. That's one of the values of this, is that you can pass it along to your friends and colleagues. We also will be sending out a survey. We really do use those survey responses to design these sessions. So please take a moment to give us your input and any ideas of topics that would be of particular interest to you. The next ARCS Forward event will be December 1st at noon Eastern time. We'll have two scholars, Edward Ander, ARCS Phoenix, and Trent Weiss, ARCS Metro Washington, who will be talking to us about self-driving cars. So thank you for attending. We look forward to seeing you in a few months on the 1st of December.